Perfect. So our next speaker today is Gilad Lerman from the University of Minnesota. So his talk is on robust group synchronization via cycle edge message passing. Okay.
Thank you, Jeff, and thanks to the rest of the organizers for the invitation and for the interesting workshop. I'm going to talk about group synchronization, which is a graph-based problem, and about a particular graph-based solution which uses the message passing approach. This work is joint with Yunpeng Shi, who just moved from Minnesota to Princeton for a postdoctoral fellowship. It is part of his PhD thesis, and he is the major contributor to this work. So I'm first going to tell you what is group synchronization. Then I will present our message passing approach. I will focus on theoretical guarantees for our work, and I'll also show you that it works in practice on real data sets. So let's start with description of a problem. So it has two main ingredients. One of them is a graph, and I have a cartoon of a graph here. And the other one is a group. And let's think for simplicity on the group SO3, the rotation group. Now, the desired output of the problem is to find a group element for each given node of the graph, which we don't know. What we know is relative information between group elements. So before, let me just for demonstration, I focus on SO3, and I don't know, I need to know rotations per node, and I kind of illustrate rotations by the action on the coordinate axis. So I don't know the rotations, but I know the relative rotations or measurements of the relative rotations. So generally, the relative group elements, or what we call the group ratios, given to element gi star and gj star is just gj star inverse. So this is kind of the group ratio. We have measurements of these. Okay, so in the case of rotations, we have measurements of relative rotations, and we need to figure out the underlying group ratios, underlying rotations. So let me make sure you're all with me. Actually, let me first tell you that it sounds like a very abstract problem, but this problem has real applications. And one of the central applications is in computer vision. For example, when you talk about the group of rotations, you want to, you have situations when you have many cameras who takes photos of a scene, and you want to get the orientations of all cameras. And now you know the relative orientations or approximation of the relative orientation between cameras, and you need to figure out the absolute orientations of each camera. And I'll talk later about applications, especially this particular application in structure for motion. But let's make sure that you kind of follow this simple problem. So let's think for a second that we have exact measurements. So each Gij here is exactly Gi star, Gj star inverse. And let's talk about the problem a little bit. So one question people ask me, do I need a directed graph? Because it's, it's Gij, so, and if I have Gji, it's different. So the point is, it doesn't matter because the Gji measurement is just the inverse of the Gij measurement in this clean case. So you know one, you know the other. But let me actually ask you to make sure that you follow what's going on here. So in this clean case, let me ask you if the solution is unique. So let's see if you can just write your answer quickly, just that I know that you're with me. I don't see. Okay, so I see some no answers, and indeed the solution is not unique because if you multiply the group elements, Gi1 star to G2 star and so on, from the right by an element G, then when you look at the group ratio, you have Gi star times G inverse Gj star inverse. So you have in the middle just Gg inverse, which is the identity. So multiplication by a right group element doesn't change the answer. So it's not unique, but if you take out this ambiguity, then you can still ask, well, is it unique? So if the graph is connected, you indeed have a unique solution. And recall, I assume now we have a clean setting where the measurements are precise. And it's not hard actually to find this unique solution. You note that if I multiply this group ratio, GI star, GJ star inverse by GJ star, I get GI star, right? So I can just use this formula, GI equal GIJ times GJ, and propagate it along the graph if you want to be, to have something more constructive. Find the minimum spanning tree, start from the root. You can arbitrarily fix it because we have this ambiguity, then use this formula along the branches and you get the group elements. Okay, so the problem is not hard when everything is clean, you have clean measurements. The problem is when the measurements are not clean, and then if you apply this naive solution, which I just described, you're going to propagate a lot of errors. Okay, so let's have a model for corruption of the measurements. And in this model, some of our measurements will be the precise measurements, but some of them will be completely arbitrary. Okay, so we have these good green edges and bad red edges. So mathematically, we partition our edge set E into a good set, like these green edges, and a bad set, the red edges. And on the green edges, the good ones, we just have the exact ground truth group ratios. And on the bad ones, we can arbitrarily assign any group element. So you can assign it with a probabilistic model and you can assign it deterministically. Okay, and given this setting, we can ask about exact recovery of the underlying group elements given these measurements of the group ratios. In order to have a solution, actually, you need to have some assumptions on the topology of the graph. A necessary assumption is that the graph with the original nodes and the good edges is connected. Sometimes when you want to prove theorems, you need to assume more. Okay, so we call it adversarial model because we can adversarially assign the group ratios for the bad edges. We can also, in some sense, adversarially assign what is the good set and the bad set, but we have some topological restrictions. Now, if it's not a good enough model for you, you can also add some noise for the good edges. And then instead of talking about exact recovery, you can talk about approximate recovery. And for simplicity, I'll focus about the noiseless case, but I'll mention something about noisy results. So there have been a lot of works in the last decades on group synchronizations. Not a lot of works on adversarial corruption. Actually, the only works on adversarial corruptions are for a different but related problem on camera location estimation. But let's focus on group synchronization, and instead of kind of reviewing all the different works, because we kind of focus on SOD for simplicity, let me tell you about previous work on SOD synchronization. So the first work is by Lanhui Wang and Amit Zinger. It was published in 2015. The model assumes a complete graph, and they corrupt an edge with a given probability Q, where we have a certain assumption where Q is less than a certain function, like this function behaves like 1 over D when D goes to infinity. And I also have values of this function where, the practical cases of SO2 and SO3. So you corrupt with this probability, and once you corrupt, you use just a uniform measure on SOD, the harm measure. So given this model, they try to see if a certain convex relaxation of the following least absolute minimization problem solve the SOD synchronization problem. And indeed, they can prove exact recovery with high probability for sufficiently large n. So this was impressive result, first mathematical result in SOD synchronization. However, we are 7 years behind it, and I think it will be interesting to have more general models, especially try to address the adversarial model. So we need to have different techniques. And before I kind of tell you about our technique, let me motivate the problem even more. So let's talk about equivalent formulation of the problem. So there are 3 simple equivalent formulation, assuming the adversarial corruption model and assuming the connectedness of the graph of the good edges. So one of them is what I just described before. We want to exactly recover the group elements. Another one, we want to just recover the good set. And a third one, we want to recover the following numbers, which they call corruption levels. So these are Sij star, which are just a certain distance between the measured group ratios and the ground truth group ratio. Now, we assume that we have a certain natural metric D on our group. We need to have a certain assumption on this metric, so it has to be bi-invariant. That is, if we take the 2 variables and multiply them either from right or left by another group element, it will not change the metric value. We also assume boundedness of the metric, and for simplicity, let's just assume it's bounded by 1. And we actually assume we have compact groups, so then we get this boundedness naturally. Okay, so let's go back and look at the equivalence. So I mentioned, these are equivalent. Maybe you don't trust me. So let me show you that 1 implies 3, 3 implies 2, and 2 implies 1. So indeed, if you know all the group elements, you can just compute, and because someone gave you the estimated ones, the measured ones, so you can just compute the corruption levels. Now, if you know the corruption levels, so then you know the good edges, because the good edges are when there is no corruption. When Sij star is equal to 0, you just check these, and these ij's will give you the good edges. Now, if you know the good edges, I showed you earlier how you can solve the group synchronization problem when everything is clean by just propagating this kind of simple formula along the graph, and the graph is connected, so you'll get the solution up to the ambiguity I talked about. Okay, so all of these are equivalent. Why do I spend time on this? Because, the first 2 formulations are very abstract, but the third one, let us work with numbers. And actually, it has an advantage because then you can do statistics with these numbers. So that's what we are trying to do here. So we're going to focus on these numbers. And in order to extract useful information from these numbers, I need to exploit the cycle consistency of the group. So let's define this notion of cycle consistency. So first of all, you all know what is a cycle, and this is just a demonstration. For simplicity of the talk, let's just focus on 3 cycles, so just on triangles with 3 nodes in the graph. So given 3 cycles, we can talk about the true and measured cycle product. So I just go along the cycle and I take either the ground truth group ratios or the measured one, and I have this product, GL star and GL. Now, for the ground truth one, I actually know that, I start with I end with I need to have the GL star is the identity of the group. This is called the cycle consistency constraint. For the measured one, it might not happen, but I want to measure the distance between the cycle product of the measured one and the identity or the cycle product of the ground truth information. Okay, so this is called the cycle consistency measure. What is interesting, but there is some relation between the cycle inconsistency measure and the corruption level. So we call the corruption level was the distance between the measured group ratios and the ground truth group ratios. And here we have a distance between the measured group cycle product and the ground truth cycle product. So what is the relation? If you fix a certain edge in a good cycle in the following way, that the other two edges in the cycles are good, then the cycle inconsistency measure is indeed equal to the corruption level. It's actually easy, and let's see why. So indeed, the cycle inconsistency is this distance. Now, the cycle product can be written as follows, because we call that jk and ki are good, so we get the ground truth information. Now we multiply from the right both variables by gij star, and we use the invariance of this metric, so it's equal. Now we use the cycle consistency constraint, so what we have here is equal to the identity, and we get the corruption level. Okay, so we call these cycles where, given ij, the two other edges are good, as good cycle. Okay, so based on the fact, we can have a heuristic to estimate the corruption levels. Okay, so we take this, either the set of all cycles or we sample a set of some cycles of interest. And now for each cycle, we compute the cycle inconsistency. And because we saw that there is some similarity, at least for the good edges that are equal, between the corruption levels and the cycle inconsistency, so we'll try to estimate the corruption levels from the cycle inconsistencies. Now, corruption levels actually live on edges, and cycles inconsistencies live on cycles. So we need to pass messages between edges and cycles. So just for illustration, I'll show you something which is analogous to the factor graph in belief propagation. So we have some interaction between cycles and edges. Okay, so how do we actually pass messages? So this is our idea, the technical idea. I try to make it simple. So we actually try to have the simplest thing. So we try to estimate the corruption levels by the weighted average of the cycle inconsistencies. And the question is how to choose these weights. So initially, we just choose them in a uniform way, in a way which is independent of the cycle itself. Okay, so for each edge ij, nij just all the neighbors of ij, so all the cycles containing ij. And we just take, initially we just take the weight to be 1 over the number of neighbors in these factor graphs. Later, we update the weights given the information that we have on the corruption levels. So we have some reweighting functions, and we actually work with, in theory, we prove things for two kind of reweighting functions. In practice, we like to use the exponential ones, but let's focus on this function. So one is the characteristic function. So what happens here, we have kind of a hard threshold here. So we have a parameter beta t, depends on the iteration. And in practice, beta t is increasing, and if you don't have noise, ideally it goes to infinity. So f is 1 if x is less than or equal 1 over beta t and 0 otherwise. So the idea is that we want to estimate, to say if we have a good edge or bad edge, and if we have a good estimate, so a variable x should be the corruption level. So if we have a good edge, we have good estimate, ideally good estimate for the corruption level, and we have 1. And if we have a bad edge, we want to have 0. Okay, so if both SIK and SJK are good, we will get a weight 1 here, ideally. And if one of them is bad, we will multiply with 0, so we get a 0 weight. So ideally, we are going to have only weights 1 for the good cycles, and we're going to have a desired mean. So let me actually demonstrate it with a figure. Okay, so I start with ij, edge ij, and I have an estimate for its corruption level from previous iteration. Now to get a better estimate, I look at all cycles containing ij, and for each cycle, for each edge in the cycle, I compute these reweighting functions. And if it's bad with this hard threshold function, I expect to get 0 usually. And if it's good, I expect to get 1. Then I multiply the 2. So here, when I have a bad, it usually will be 0. When I have 2 goods, it will be 1. So when I use the softer thresholds with exponential function, I usually see high weights for the good cycles and low weights for the bad cycles. Now I average the cycle inconsistencies with these weights, and I get an improved estimate for my corruption level. So before I move on, let me just tell you that it kind of reminds of a neural network. So we have the linear part here, and then we have nonlinearity here with somehow different architecture. So we look at all the neighboring edges in a cycle, in all cycles. So then so this was actually the basic idea. Let me see if there are any questions before I kind of move on. I don't see any questions, but maybe I don't see the full screen. But Jeff, if you see any question, let me know. Okay, so what I would like to do then is to kind of explain why this very, very basic idea works. So I'll start with an explanation for the physicists and then an explanation for mathematicians. So why do I actually want to address the physicists? Because all of these ideas of message passing and belief propagation are related to physical modeling. And what physicists like to do, they like to have assumptions on generating certain models and then kind of show that they make sense and get interpretation with these assumptions. So here, we assume that our reweighting function, and let's from now on, at least for the theory part, assume that the reweighting function is the hard thresholding one, is the probability of having no corruption given the estimates of the corruption levels at iteration t. Also, let's assume that each node has at least one good cycle. And then we assume that these random variables are IID, and we have the following independence. So given this assumption, it's not hard to do the following exercise. You can show that the weight that we have is actually proportional to the probability that L is good, a good cycle with respect to Ij, given the corruption levels at iteration t. I think I should have here t plus 1. Yeah. So we got conditional probability that L is good. Now I told you before that if L is good, then you have the equality DL equal to Sij star. So let's assume that both are equivalent, and we can have some model under which, if you have a good cycle, having a good cycle is equivalent to having the cycle inconsistency equal to the corruption level. So then we have a Wij is just conditional probability of having this equality. Looking at this formula, we multiply by DL. It means that Sij at t plus 1 is just the conditional expectation of the ground truth corruption level. Okay, so it gives us a very nice interpretation of what we get at each iteration. You can go further, have a more complicated model, and kind of interpret the reweighting function in terms of some probabilities. I don't want to get into these technicalities here. Let me just say that in usual modeling of belief propagations, there are stronger assumptions. You need to assume how the density functions look like. We actually don't need it here. The other thing is that we actually, all of this is just for kind of intuition. But when we have our mathematical theory, we don't need these strong assumptions. So let me show you how the mathematical theory looks like. So the mathematical theory says that under an assumption, and I'll explain it in a second, and with a certain choice of the parameter beta t, so here we just have we actually form a geometric series with certain values of r. So then our computed estimated corruption levels converge to the ground truth corruption levels with a linear rate of convergence. Okay, so it's a very clean theorem, but it has a certain assumption, which is here. So lambda less than 1/4. So what is lambda? So I denoted by Gij the set of all good cycles with respect to the edge ij, and Nij is all cycles of edge ij. So Bij is the rest of the cycles, which we call bad. Now let's look at the fraction of bad cycles over all cycles for edge ij, and let's take the maximum of this among all edges, and we call it lambda, which is kind of maximal ratio of bad cycles. So the theorem says that if this ratio is bounded by 1/4, then you get this nice convergence to the desired solution. Now, I won't show here the proof, but the proof is rather immediate. So you recall that Sij is a certain average, and you can write also Sij star at the certain average by taking limits, and then you can look at the differences of these two averages and just do some direct calculation, and it's like a one-page proof. Now, the main question is how we can generalize it. So one case is where we have noise. The other one is, cases where we want to really take lambda to go to 1 with different assumptions. So let me first say something very quickly about the noisy case. So we can change our model. So we leave it adversarial for the bad edges, but now for the good edges, instead of having the exact ground truth group ratios, we add noise to them. And we have some theory for Gaussian noise, but let's now talk here about the theory for bounded noise. So we have a certain parameter delta, such that the distance with the noisy version and the ground truth one is less than delta. So under this model, we can still have somewhat similar theory of lambda less than 1/4. We have convergence, but not linear. We have certain choices of a parameter where what's going on with beta t. Initially, they go up geometrically, and later they stabilize. And what we can see that in the limit, the bound between the estimated corruption levels and the ground truth one is bounded by something of order of the noise. Okay, so you have near recovery up to the noise level. You can't have exact recovery. Now, the most interesting thing is, can we look at setting where we push lambda to go to 1? We really have very, very high corruption. And for this, we follow kind of a common uniform corruption model. It's similar to the one of Lanhui and Mitzinger. So we have, instead of having a connected graph, we have an Erdos-Renyi graph where with parameter p, which is the connection probability between edges. Okay, so we randomly pick edge with probability p, and and we randomly connect an edge in graph with probability p, and then given an edge, we corrupt it with probability 1 minus qg, but now the corruption is not adversarial, but it's uniform. It's from the harm measure on the group. So we want to have theorems with very high corruption. We want actually 1 minus qg to be able to go to 1 under this setting. And the theory is a little bit complicated. So let me demonstrate it for the group SO2. And just another review of the model. So now we have kind of the correct information on the good edges, and on the bad edges, we have the harm measure, the uniform measure. So what the theorem says is that if you choose any probability p for the Erdos-Renyi graph, so if you want any sparsity of your graph, and any good corruption level or any bad, or any 1 minus qg, so 1 minus qg can go to 1 to be close to 1 as you wish, and then you generate data according to this uniform corruption model. And if you choose beta 0 and beta 1 in a certain way, then and then have a geometric series for the rest, then with high probability, you still get this linear convergence of our estimated corruption levels to the ground truth ones. So if you want to talk about more general groups, you need to have some more definitions and have kind of a more general theorem, but I would rather explain it for a simpler case, especially that things can, different things can happen with discrete groups. So just to put things in context, let's go back to the previous theorem that I reviewed of Lanhui, Wangel, and Mitzinger. So their theorem was about SOD synchronization, and we can talk about any compact group synchronization. They did not address adversarial corruption, while we had a theory for adversarial corruption. For the uniform corruption, they assume a complete graph, and they had a certain restriction on their corruption probability, or here it's the good probability. We can have any corruption probability and Erdos-Renyi graph. Any questions so far? Okay, so let me show you that this simple idea with clean guarantees work for real problems. So the problem I'm interested in is called structure for motion. It's a very essential problem in computer vision. So the problem assumes a lot of different 2D views and different photos of a given scene. Here we have a Colosseum from different perspectives, and as you can see, some of the figures actually have a lot of occlusion, like we don't focus on the scene itself, but on other objects there. And given all these photos, we want to construct 3D models of the scene. Okay, so given all these photos, we want to get something like this. So there is a very well-known pipeline to solve this problem, and it has a lot of steps. Here we only care about one of the steps, which is estimating camera absolute rotations from relative rotations, which is just the rotation synchronization problem, or SO3 synchronization. The issue is that because we have this kind of long pipeline, the estimates that we get for the relative rotations are pretty bad. Especially, the issue of key point matches gets a lot of noise here and they accumulate. So we get pretty bad relative rotations, and we need to estimate, given them, we need to estimate the absolute rotations. So let me tell you first what is the state-of-the-art solution. So state-of-the-art solution uses IRLS, iteratively reweighted least square solution. So it tries to solve the following minimization problem with p equal 1 or p less than 1. We take distance between kind of an estimated group ratios and the measured group ratios. And the solution via IRLS, oh, by the way, D is the geodesic distance on SO3. And the IRLS, what it does, it actually try to replace this LP minimization with weighted least square minimization with choice of weights, if you kind of plug it in. But we look, when you add everything together, it looks like d to a power of p of this, but there is certain changes because you kind of estimate it given what happened at previous iteration. You fix RJ at a given t. Now, this is it's a highly common solution, and it seems to work nicely, but it has some problems. Let me just also mention that, solving the weighted least square problem is not easy. It's a non-convex minimization, and people have a certain method for this called the algebraic averaging. So it's not usually, it can run into different problems. A big problem is that it can overweigh bad edges. So it's possible that, for the bad edges, I can still have small residual here, which will result in very high weight. And actually, I want low weight for the bad edges. Another thing, I'm using this Lie algebraic averaging, but it may actually not be great approximation when I have high corruption, but just approximation for the underlying problem. And also, it's possible that in the case of very high noise, I will get a non-negligible weights for outliers. So ideally, for outliers, I want 0 or close to 0 weight. But when I have a lot of noise, I may have higher values of weights for all the points. So let's focus on this main problem, that IRLS can overweigh bad edges, that the residuals can be small. So let's recall, okay, we have these kind of iterated, so weighted least square problem. We solve for the rotations, and now we estimate the residual, and then we use a certain function f to get weights, and we kind of repeat it. This is the way IRLS works, and we kind of criticize this step. So we can actually take away this step and use what we call a message passing unit, and have a very similar idea to our previous algorithm to CAMP. So given the residual at iteration t, we improve it by looking at all the neighboring cycles and having a similar nonlinearity, and then and weighted average to get a better estimate for the residual, and then apply it within similar function and get weights, and then repeat it, and so on. So we call this message passing least squares algorithm, or Minneapolis algorithm. So just to say how we initialize it, they say, the weights and initial rotation initialized by CAMP. So what do I mean by this? We apply the CAMP algorithm. Camp only gives me corruption levels. So now we have the graph whose weights are these estimated corruption levels, and we find the minimum spanning tree of this graph. And I told you earlier, we can, given this relative information, we can propagate it along the graph and get the underlying rotation. So this is our camp approximation, just for initialization, and then we apply the whole procedure to improve our estimate. So we see, and I'll show you later, in practice, we see the big improvement. And one of the reasons is that we kind of take advantage of neighboring information. You know, maybe we got a very small r by mistake, but now we look at all the cycles and we can take advantage of the other estimates and improve our estimate. So indeed, we often see lower weights for the bad edges or higher H's, where R can be really, really small or the weight can be large for I or less. And we have some interpretation for this as the conditional expectation as before of the corruption levels given these R values, the residual at iteration T. We also kind of see improvements of the other problems, but I don't want to get into technicalities here. Instead, I want to show you some results. Let me skip the synthetic result and focus on real data results. So I told you the problem. So we have kind of different data sets of different scenes. So here we have photos of the Notre Dame, but we have several other scenes. And these scenes are part of the phototourism data set. We follow a certain pipeline how to actually assign an error of our method. The pipeline is by Noor Zisil and Mitzinger. And let me just jump into showing you the errors that we get versus the state-of-the-art errors. Okay, so these are the different scenes that we have. These are the two previous RLS methods, and we show the error and the runtime. So when we just apply camp with this minimum spanning tree idea, we still get fine result, not as good as the RLS one, but with much better runtime, or better runtime. The Minneapolis algorithm can significantly improve the errors. So for most data sets, it gives the best errors. And even if not, it gives kind of close errors, maybe except for the Gendarme and Markt in Berlin, where you have actually two identical buildings. So it's really hard for a global method to find the correct solution. Right, so I showed you then very strong results on real data set. We also now working on permutation and synchronization, and we have some result for key point matches. So in general, we have completely novel method to solve the group synchronization problem, and we can actually guarantee it for adversarial corruption. And it's a unified method for any compact group. We had different mathematical results, and we also showed you that we have a competitive version for real data set, especially for rotation synchronization. There are several open problems. It will be desirable to get sharper estimate for the camp algorithm, especially, you know, we had L infinity bound on the bad corruptions. Maybe you can do something better and allow some higher corruptions in local regions. We also don't have yet guarantees for the Minneapolis framework, but only for the camp framework. It will be nice to extend the work to other reweighting functions and optimize their choices. And possibly even have parameter-free implementations. And it's also possible to extend this work beyond group synchronization. For example, we see immediate extensions to the camera location problem, and actually this problem started with camera location problem, and then we kind of saw cleaner theory for the group synchronization problem. So let me just quickly review our existing work. So the initial works, which seems kind of unrelated, is about the camera location problem. The main mathematical work is on the archive. The application to rotation synchronization just appear in ICML, and we also have a preprint on applications to multi-object matching, where we use permutation synchronization, and there's some interesting things about how things apply for the discrete group of permutations, and how you can see very direct relation to the graph connection Laplacian in our method. Okay, thank you.
Okay, thanks for the really fascinating talk. Are there any questions from the audience?
I have a question I can ask. So I think the answer to this is probably hidden away in theorem 3. So what I want to know is, can you tell me what the minimum number of good edges you need for the method to work?
Okay, so you said in theorem 3, but theorem 3 is for a very specific model, right? So here, and actually, can you repeat the question again? I just want to be completely sure.
So sure. So okay. So I mean, I'm happy to work in the regime of this model here. So in this model here, can you tell me what is the minimum number of good edges you need? So I think this should be given in terms of this sort of QG parameter.
So, right. So here, as you can see, QG can have any value between 0 and 1. It will just affect our probability estimates. You will need very, very large N to make it work. But in theory, we can work with any fraction for this particular model.
I see, but I guess, okay, if you let QG depend on N, then I guess you can look at the probability estimates, and then you can let QG converge to 0, I guess, and then that will tell you sort of, okay, asymptotically, that'll give you a lower bound.
Right. And because we work with general synchronization, we don't get the information theoretic bounds in terms of the dependence on N on QG. So I think, you can improve them, but it's still not so trivial to be able to work with any QG between 0 and 1.
Do you know if these results are sharp in the sense that, okay, so like I just said, you have a lower asymptotic bound on QG, but I mean, if QG is, yeah, I guess okay, so if QG is too small, I mean, do you know that this theorem is sharp and that you won't get?
Okay, so in terms of kind of the information theoretic bounds, the only work I know about is for Z2 synchronization by Emmanuel Abbey and Bandera and Zinger, and I think I forget one of the co-authors. So we don't match their information theoretic bounds, so we don't get a sharp estimate. But we had kind of very general estimates for any group. It's possible that we can sit down and check how to improve our estimates for Z2 and get better estimates. I'm not sure if the information theoretic ones, but we may improve our estimates for a specific case. But we are not there. We don't have the sharpest estimates for Z2 synchronization, where I know what should be the sharpest estimate.
Okay, there's also a question from Nicholas. I'm gonna try to unmute you, Nicholas. All right, I'm clicking. Okay.
Thank you, Jeff. And thank you, Gillette, for your nice talk. Can you hear me, first of all?
Yeah.
Yes, we can.
Okay, great. So my question is, in this applications and the real data applications, so what is the graph there? Is it a complete graph, or?
So yeah, so here actually all. So I think as far so it depends on the key matches. Because as long as so what happens, someone has to, given two images, you need to compute key point matches. So it depends. It's not a complete graph, because if I know, let's look at this figure. So if I look at these two photos, like photo here and photo here, do you see the photos I show you?
Yes.
They don't have any key point matches, right? They have very different parts of the scene. So they are not connected. But if this photo and this photo,
yeah,
they are connected, right? Because
okay,
key point matches.
Right. But it's essentially a pretty dense graph. It's not very sparse, let's say.
So it's really, actually, it's a good question. I'm not complete. I expect it to have some density, but actually, it really depends how, about how, about the different views. I would assume that actually you have some certain areas of the scene where you have a lot of, density there, because people like to take photos of these kind of special parts of the scene. But there should be some areas which are sparse, that, are not connected to a lot of other areas. But yeah, it's a good question, because I recall that we had some issues about sparsities. So but I never checked if the actual graphs are sparse or not. So I have to check it. I'm not sure.
Yeah, it's just that, of course, I mean, to me, it's almost like, it sounds like a cyclic kind of argument, and I mean, for this application, because it's almost like saying, we have a lot of pictures of already areas that we understand. And so, okay, we know that they're essentially the same area. So what is the synchronization problem? And so I mean, I was just wondering for this specific application, so how things work. But yeah, thank you for the answer.
Okay, any other questions before we go to the breakout room? Okay, so thanks for the talk again, Gilad, and we'll go to the breakout room for further discussion. And let me also mention that there's a break after that, so the next talk is not until 12:30.